Hello everybody, it's Danielle Weigel here again to finish part B of our third and final exam for the class Transport 2. In this video we will be deriving the differential equations for the mole fraction of the water vapor in the air and the temperatures of air and water in a cooling tower. In our next video we'll take care of B2. So we have this cooling tower set up that has a gas flow rate flowing in from the bottom and coming out the top, and we have our liquid running down from the top to the bottom. We can see that we will end up having different temperatures in the inlet and outlet for each of these, and we are going to define the position of positive z going downwards following the flow of our water. We have our specific area, our specific volume, and we also have our specific area, and then we also have our cross-sectional area defined here. Our gas flow rate and our liquid flow rate will be defined as using kilograms per meter squared seconds, just because that's going to make it easier for us later. Our first differential that we are going to be working through is the change in mole fraction of the water vapor in the gas flow. So we want this, and the first thing that we need to look at is what's changing in this gas flow, what's changing in order to get this. We first have the gas flow rate is going to change as more water vapor is added into the stream. And that's going to change the average molecular weight, which we're going to define as m. The mole fraction will of course change, and then because we defined our gas flow rate with meters squared per second, we also need to include the cross-sectional area. Then we need to look at why is the system changing, and that is going to be due to mass transfer. So we can look at our mass transfer coefficient times the difference between the concentration at the liquid gas interface minus the concentration of the system, of the environment. And then we also need to include our specific area and our cross-sectional area to show that these will be changing over the course of our position as the gas rises up through the cooling tower. So we need to make sure that this term is actually equal to the molar flux of the water vapor, and we also need to keep in mind that this can also be written in terms of partial pressure. So that would look like this. The partial pressure of the concentration at the interface would be the saturation, the partial pressure of the saturation, because right at that liquid gas interface, that's what the partial pressure is going to be, over the gas constant times temperature. And then out in the environment outside of that is going to be the total pressure over the gas constant times temperature. So that is our molar flux. We don't need that right away, but for this problem, but it'll help us later. So now we can go ahead and take our constants out of this differential. We are going to assume that the gas flow rate over the average molecular weight is going to be constant over as we go along z, because it's really not going to change enough where it's going to be significant. So we can consider that a constant, and of course our cross-sectional area will remain constant. So that will give us cross-sectional area times g over the molecular weight dy for the change in our mole fraction, and then that's equal to the molar flux of the water times the specific area times the cross-sectional area as it changes over along Z. When we look at this right here, we define the change in Z as positive going downwards, but we are looking at the gas flow here, and our gas flow goes upwards. Since we defined our molar flux in this way, where the concentration at the interface will be higher than that at outside of the interface, this will end up being positive, and so we need this to end up being to include a negative sign to account for the fact that this is going in the opposite direction as to what we define positive Z as. Now we can go ahead and cross these out and rearrange our equation in the form that we actually want, which is dy dz equal to negative specific area of the molecular weight over the gas flow rate times the molar flux of the water. Now that we have our first differential equation defined, we are going to be looking at the next one, which we will be using the temperature of the liquid for. Whenever we think about changes in terms of temperature, we also need to be thinking of changes in terms of enthalpy. So if we look at what contributes to the change in enthalpy of the liquid, we know that what we'll be changing is the gas flow rate, and along with that we need to include the cross-sectional area, since we define that as kilograms per meter squared seconds. We also need to include the heat capacity of the liquid. This is supposed to be an L. As well as the actual change in the temperature of the liquid. Then when we look at what's contributing to this, we need to include the both the heat transfer and the mass transfer. So the first one that we're going to be looking at is the heat transfer. So we have our heat transfer coefficient, and then the temperature of the gas minus the temperature of the liquid. And then we have to include our specific area and cross-sectional area as it changes over Z. And then we also need to include our mass transfer. And similarly to how we did in section A, as well as with our definition that we defined up here, we are going to be defining that as the heat of vaporization times the molar flux of the water. And then once again we have to include our specific area, and the change over that, the change over Z. So now we can go ahead and take out like terms and rearrange the equation in terms of dTL over dZ. And we want this up here. So our like term over here is going to be this right here, the specific area, and then these like terms will also apply. So we will have this out front, and then our heat transfer section and our mass transfer section. And that gives us our second differential equation. Now that we have our second differential equation, we can go ahead and move on to our third. I'll box this in. And the way that we're going to solve for this third one is dependent upon the fact that the system is considered steady state. And what this means is that the enthalpy of the change in enthalpy of the liquid should be equal to the change in enthalpy of the gas. And that is because that is steady state. So now we can go ahead and solve for our change in the enthalpy of the gas. And when we look at what's involved with that, we have the gas flow rate, of course, times the cross-sectional area. We also have the specific heat of the gas, as well as the temperature of the gas. And then we also have to include, as an addition this time, the heat of vaporization, as well as the cross-sectional area and the gas flow rate over the molar mass, because the mole fraction is also changing. So we have to use these to cancel that out, to transfer this from kilograms to moles, and this to get rid of our meters squared. That was implemented by the gas. And since we have this as our definition of our enthalpy of the gas, then we can also set it equal to, just like we discussed earlier, the enthalpy of the liquid, which we wrote up here. So we can rewrite that real quick. And I'm just gonna pull these out. And we can once again see that all of our cross-sectional areas will cancel out. And these are constants. These are constants. So this will end up being that and this. And since we pulled this out, we can go ahead and move this over here as well, so that we end up having this over here. And when we look at this differential equation, we can recognize that we already solved for that up here. So we can go ahead and replace that. And then notice that these cancel out, leaving us with this term being the heat of vaporization, the negative heat of vaporization times the specific area times the molar flux of the water. And then when you look over here, you can see that this same term exists, which means that these cancel out. Next, we can isolate our differential equation that we want, and that will look like this, which will give us our third and final differential equation that we need to solve for. Using these three differential equations, I can go ahead and plug them into Python so that we can complete the second part of the exam problem in graphing out our plots of the water temperature, air temperature, and water partial pressure as a function of the position in the cooling tower. So we'll do that in the next video.